In this video, we're going to be talking a little bit about our acid-base indicators of how we know when to use which indicator. So we can use an indicator to signal that we've hit the equivalence point in a titration. And remember, indicators are dyes that change colors at different pH ranges. The endpoint of an acid-base indicator is the pH of that color change. So remember, equivalence point was referring to a volume where we're going to notice that color change. The endpoint is the pH of that color change. So when we're performing a titration, we have to select an indicator with an endpoint approximately equal to the pH of the equivalence point of the acid-base reaction. So we need to make sure that we pick an appropriate indicator, or we will not see a color change when we're supposed to. So if you remember, all of our acid-base indicators have a different range for color change. So we've used phenolphthalein before, which goes from being clear to pink, more at a range of about 8.4, 8.5. We've also used in some previous reactions. You may have seen a difference in phenol red. This is one that we've done in Chem 1. It goes from being a yellow into a red color. Chem 1, we also looked at bromothionyl blue, which goes from being yellow to blue. So depending on where our target pH is for that equivalence point, whether we're dealing with strong acids and strong bases, or if we have a weak acid or a weak base, we would want to make sure to look for the appropriate pH in terms of indicators. Usually our acid-base indicators are going to be some form of weak acid, but they can also be a weak base. And these are going to show distinctly different colors between their non-ionized form and their ionized form. So here's an example of where the acid form would be red and our base form, the ionized form, would end up being blue. So that would be the color change that we would be looking for. So as we increase hydrogen, equilibrium would shift towards the left, producing more of the acid form, the unionized form. So we would see this as red whenever we're doing a titration. If we were to add base to this, remember hydroxide is going to react with hydrogen, so reduce the hydrogen we have. This would shift equilibrium towards the right, producing more of the ionized form, the conjugate base, so we would actually see blue. So this sample indicator would turn red whenever we add acid to it and turn blue whenever we add bases to it. The color change where we're going to see the endpoint is going to occur when moles of acid equals moles of base. So that's going to be right where that color change is going to occur, where it will shift from blue to red or red to blue. And whenever those are equal, the pH of the solution is equal to the pKa of the indicator. So when we're picking appropriate indicators, we want to look for the pH of our equivalence point should be equal to the pKa of the indicator. So that's how we would determine which indicator is appropriate for a certain titration. Now, indicators all change color at different pH ranges because every weak acid indicator has its own Ka value. Therefore, its pKa would be at a different value as well. So the pH range is dependent on the indicator's acid strength. That's why some of them will be used for lower pHs or higher pHs. When selecting an appropriate indicator for a given titration, you need to select an indicator with an endpoint approximately equal to the pH of the equivalence point of the acid-base reaction. So you want to make sure that the pKa of the indicator is approximately equal to the pH of the equivalence point. And we generally say that the endpoint should be no more than 1 pH unit beyond the equivalence point. So if our target pH is 3.5, we would want to make sure that the indicator's target pKa is between 2.5 and 4.5. The closer to 3.5, the better. And some indicators you'll notice have two separate endpoints. And these are going to be ones that will be used for our diprotic weak acids. So they actually have two Ka values, therefore can produce two color changes.